Hello, everyone. Welcome to this session. And my name is Frank Wei, and I am a tech lead at General Motors, and I'm going to moderate today's session for Dr. Tim Hesterberg. Dr. Tim Hesterberg is a data scientist and Instacart with previous experiences as a data scientist experience at Google. His career has spanned multiple domains, including positions in academia, energy, and software development. He earned his PhD in statistics from Stanford University and his bachelor in mathematics from St. Olaf College, and also spent 2 years studying in Germany. Dr. Hesterberg is co-author with Laura Chihara of Carleton College of Mathematical Statistics with Resampling and R, a widely used text in statistics education. He has also contributed to instructional materials on teaching introductory statistics using resampling methods in collaboration with colleagues, including David Moore. His research and applied work covers a wide range of topics, including statistical methodologies, electric demand forecasting, web traffic analysis, clinical trials, display advertising, computer vision, and natural phenomena such as streams and earthquakes. And he has also served in leadership roles as the Canadian Statistical Sciences Institute and the National Institute of Statistical Sciences, and was a contributing author to American Statistical Association's guideline for undergraduate statistics program. And he is also a role model for a lot of people, including myself. I have personally learned a lot of things from his webinars and lectures. And today, he's going to cover the covariate and adjustment, introduction to the resampling and surprises. And the stage is yours, Dr. Hesterberg. And let's welcome for his presentation.
Okay, thank you, Frank. I'm happy to be here. Thank you all for joining. Frank didn't mention my one mathematics publication, which was a very serious one. It was spiders walking around spaceships, a geometric interpretation of the derivative of sine and cosine. Today, I'll be talking in kind of three parts. I'll talk first about covariate adjustment. Then I'll talk about an introduction to resampling. And then we circle back and combine both of those, talking about applications of resampling for A/B testing and covariate adjustment in particular. First, a little bit about Instacart, where I currently work. It's a relatively small company, but it's a complicated company. We have a four-sided marketplace. We have customers who place orders. So you would like something delivered from a local grocery store. You use the Instacart app or website and place an order. We have shoppers, gig workers, who go to the store, pick what you wanted, and deliver it to your home. We have the retail partners, and we have advertisers. And the money that they pay lets us keep prices lower for customers and pay shoppers more. It's complicated, and we are continually trying to optimize this. For example, you place an order, we won't show that to shoppers right away. We'll instead wait a bit to see if we can combine that order with somebody else's order into a batch, two orders, maybe from the same store, being delivered to nearby addresses, and have a single shopper deliver both orders together. So this increases our efficiency. Well, how long should we wait to batch orders? Once we show orders to shoppers, at some point, if the order isn't being picked up by shoppers, we may increase the pay that we offer to shoppers. How quickly should we do that? How much should we increase the pay? So we are continually working on different ways to optimize our system, improve the quality of orders to customers, reduce the costs, reduce the driving time for shoppers, many experiments, and it's a fun place to work. If you're interested in working there, I have an advice doc that Frank can share in the chat. And you can also contact me on LinkedIn and I'll send you the doc. Moving on to covariate adjustment. What is it? Why are we doing this? Well, we're doing lots of A/B tests, and we will assign customer, shoppers, geos randomly to treatment or control. And on average, they're balanced. Similar treatment control, so it's unbiased. This is well known. Oh, but there are random imbalances. So say that we're interested in running an experiment that we hope will increase the amount that customers spend per order. Well, it could happen that the treatment arm happened to have more heavy users, people who spend more. Now it's biased. Wait, I just said it was unbiased. Now I'm saying it's biased. What's the deal? You gotta be careful when you're talking to a statistician about bias because it can mean different things. And here's an analogy. You've got two kids and you go and buy 2 ice cream cones. And you tell the kids, I'm gonna flip a coin and whoever wins the coin flip gets both ice cream cones. Okay, so one kid now has 2 cones and the other 0. And the one who has 0 says, this is unfair. And you say, you had the same chance as your brother. Okay. By one definition, that is unbiased, it's fair, but in practice, no. The kid is not going to be happy. That's the deal here. Once we see that the treatment arm has more heavy users, the results are now biased, given the additional information that we have. Covariate adjustment corrects for this. We correct for imbalances in key covariates. For example, GTV is gross transaction value, it's dollar spend. This is something that we care about. We might look at the GTV in the pre-period before the experiment starts and balance that to make sure that we have similar heavy users in both groups, or correct for imbalances. So we are eliminating conditional bias, and in doing so, we get smaller variance and a better signal-to-noise ratio. And because that better signal-to-noise ratio, we can run experiments faster. For our experiments, it's typically about 67% faster. So this technique is common in data science and the tech industry. And here's how it works. Take a look at the picture. Here, X is the pre-period measure. This might be average spend per customer in the pre-period. And Y is what we're interested in, how much they spend during the test. We have the red points corresponding to treatment group customers and the black points corresponding to control group customers. On average, the X for the treatment control should be the same because we're doing random assignment. But here we see some imbalance. And actually, the imbalance here is kind of exaggerated. We would not see imbalances this great in real life, but this is better for the visualization. So we see, first of all, that within each group, there is positive correlation. The more people spend in the pre-period, the more they spend in the post-period. We also see that the treatment appears to have an effect. The red points are higher than the black points. But there's also imbalance. So if we were to just take the difference between the Y bar for the treatment, which corresponds to the beginning of the arrow, and the Y bar for the control, which corresponds to the beginning of the black arrow, that vertical distance is not a fair assessment of the effect of the treatment because it is confounded with the difference in the means of the two groups in the pre-period. So we correct for that by fitting a regression. and predicting what the average of the treatment group would be if the mean of the x's for that treatment group were equal to that common mean, x bar. And we did the same thing for the control group. So a better estimate of the effect of the treatment is the difference between the ends of the arrows. So our prediction for the control group is the regression line at the common x bar. And you can also write that algebraically as the uncorrected average minus the regression coefficient times the difference, the deviation between the observed mean and the overall mean. And similarly for the treatment group. And another interpretation of this is that that difference between the treatment and control means is equal to the average across all of the data combined of the difference in predictions. And this particular interpretation is useful if you're doing something other than a linear regression model. Suppose that you were doing Poisson or logistic regression. The formulas based on linear regression don't work, but this interpretation still works with logistic regression. And finally, another interpretation is that we're reweighting the data to the common mean. We know that in the population, if we didn't have random assignment, there's no difference in means between treatment control people. So what we do is we weight the observations. For the control group, we had too many observations over on the left and too few over on the right. So we give the observations on the right greater weight, those on the left less weight, so that the weighted mean of the x for the treatment control group would be equal to x bar. And similarly reweight the treatment group observations. And by reweighting, we end up with the same estimate as the algebraic approaches. At this point, are there any questions? Okay, and I'll make the comment that a nice thing about covariate adjustment is it gives data scientists in tech the opportunity to make a positive contribution. All too often, we are sort of put in the role of gatekeepers. No, your treatment didn't work, sorry. Or no, you can't analyze the data that way. Here, what we get to do is actually improve the experiment velocity, give more accurate answers, not just say no. Moving on. The variance reduction that we get is proportional to R squared, the variance reduction in the experiment. So if we have a 67% variance reduction, experiments run faster, 2/3 faster. The way we calculate standard errors is the standard error for the delta hat is the residual variance squared divided by the number of control observations plus the residual variance for treatment over control treatment observations, and then taking square root of that. So fairly easy to calculate the standard errors. A nice thing about this is we don't need a lot of complicated math to do this. And for more details on this, you can check out a blog post that I have with Ben Knight. Okay, were there any questions? Is there a question from Amy?
Yes, Amy, please. Amy, you are muted. Please unmute yourself.
Oh, hi.
You're double muted again.
Hi, I didn't have a question.
Oh,
Okay.
Okay, and then there's two questions from the Q&A session. Actually, three. What size of A/B tests are you typically running? How many customers are from Italy?
Um, I am not going to share a number of customers, but the A/B tests are typically large, except when the experiment has just started, then the number of observations that we have is not very large. But ultimately, we tend to have pretty large numbers of observations for experiments that are run at the customer level or at the shopper level. On the other hand, we run many experiments where we randomize different geographic regions into treatment or control. And those have much smaller sample sizes, on the order of 2,000.
And another question from anonymous attendees, what is the link to the blog post? And we're going to share that later on. And then move on to the next question is from Jeffrey Cornsburn. Can we get a, oh, so the question is deleted. Please move on, Doctor.
Okay, great.
Yes.
Hey, thank you. Okay, one caution in doing this, you cannot use an X variable that's actually affected by the treatment, because we are assuming when we do this that the true mean of X for the treatment group matches the true mean of X for the control group. So if there is a difference in means, and if that difference is more than we expect from randomness, it's good to track down why the difference occurs. So in our experimentation platform at Instacart, we automatically do these checks, but we do them at a significance level of 100 times smaller than the usual 5% alpha. And the reason for the small value is that we don't want a lot of false alarms. But even though this looks like a really small number, it is still easy to detect real differences. That alpha equals 0.005 corresponds roughly to a z-value of 3.5, I believe, as opposed to the usual roughly 2. So it's not a huge deviation. If there is a real difference, we can still detect it, but we reduce the number of false alarms. Now, some examples we've observed where we get imbalance at Instacart. One is when we are looking at variable contribution to profit per user. And the X might be the pre-experiment VCP, but that can actually be affected by the treatment. So we have the pre-period where the customers are placing various orders, and we calculate a VCP for each of those orders. But after the experiment starts, the VCP for those orders could still change because there might be, the customer might complain and we might give the customer some appeasement, or there might be some problem with the credit card charge. So even after the experiment started, the VCP per orders could still change. So we can't use that VCP per user in the pre-period as a covariate. Another example that we have is bot filtering, where maybe the variant, the new treatment that we're doing might result in faster calculations, less latency. And as a result, the total time for orders may change, and that may affect our bot filtering, so that we actually end up with different observations in the treatment control groups. So then we've got some imbalance that we have to deal with. Third example is when GTV per order, when the number of orders is affected by the treatment. For example, if we do incentives, if we give people coupons. Now, a complication that we have at Instacart is that our data is too large to do the regression. We access our large databases using SQL, and we want to do covariate with multiple X variables, not just the pre-period variable, but various other things that may predict the outcome. And you can't do multiple regression in SQL. Well, there is a way, but it's really ugly. You don't want to do it. What we do is we do a regression on a random subset of the data. So pass that to Python, do the regression. Then, if we just used those coefficients as is, we would get lousy results. It would be equivalent to running the whole experiment based on just that subset of the data and throwing away the rest of the data. So instead, what we do is we use most of the coefficients from that regression. We use the slope coefficients, but then we re-estimate the intercept coefficient using all of the data. So the new intercept coefficient is the average across all of the data in the control group of the y minus the predicted value, and similarly for the treatment group. And it turns out that, doing the random, getting the slopes from a subset is almost as good as doing the regression on the whole data set. We're losing very little accuracy by doing this. It's the intercept coefficient that we really want to get estimated accurately using all the data. Another complication is that our observations are often not independent. So if we're interested in dollars per order, we have the complication that orders are not independent because users place multiple orders, and a user that makes one large order tends to make other large orders. So GTV per order is the sum of all GTV values across all orders divided by the number of orders, or we can write that as what is the GTV for a customer and the number of orders per customer. So we can rewrite that as the sum of yi over wi. And now yi is the value for a customer. So now the y's are independent and the w's are independent. So we can express that as a ratio y bar over w bar. And then now we have independent observations. We can get the standard error for this ratio using the delta method. And again, see the blog post for details on using the delta method in this case. I will mention it a little later in this talk. I'll talk about doing this using resampling. And we've got a complication that clustering is expensive. We have a lot of customers. And to do these calculations, we need the values for each customer. And a snippet of the SQL from that is that we need to get the sum of dollar values per customer and the number of orders per customer grouped by the number of users. And because there are a lot of users, that calculation is expensive. So we will use resampling as an alternative to do that. So we do this, Google does it. Basically, you put each customer into one of 128 buckets. We hash the user ID to do this. And then instead of grouping by customer, we group by the bucket. So a much cheaper calculation. I'll talk more about that particular calculation later in the talk. And another complication that we have is trade-offs. The delta method calculations that you can use to get standard errors for any metric don't give us standard errors for linear combinations like A times growth minus B times cost. And getting all of the different standard errors for combinations that we might be interested in would get really ugly for all the different combinations. And with the resampling approach, it's pretty easy. We get 128 values for growth, 128 values for cost, and they've got some correlation. So it's easy for us to calculate standard errors for linear combinations like this. Okay, this is the end of the section that focuses on covariate adjustment. Are there any questions at this point?
We have some questions from the Q&A session. And the first question is, can we extend the effect estimate when there is more than one covariate from Alan Vasquez?
Yes, there's no limitation to one covariate. Here I wrote things in terms of a single X, but all of the formulas extend naturally to multiple regression.
And from Charlie Michel, can you explain the process of how you arrived at alpha 0.0005? I'm hoping for guidance on how to determine this for other projects.
It's not really critical. Well, we picked 0.005 as something that would result in not many false alarms and something that would still have a reasonable Z value so that we could detect real differences. And frankly, if you were to make that 0.0001 or 0.001, it's not going to make a big difference. This is not a sensitive issue, sensitive coefficient.
Yep. The next question is, what is GTV from Daniel Alvarez?
GTV is dollars. It's gross transaction value.
And do you do a sensitivity analysis for the subsets for the regression analysis? I assume you'd get extreme values from the subset and would skew the slope estimates from Miguel.
We typically use 60,000 to 1 million observations for the subset. So it's still a reasonably large sample so that we get reasonably accurate data estimates.
Yep.
But it's much smaller than the whole data set size.
Yes. And the next question is unbalanced sample size a problem for your standard error calculation from Yijun?
So there are two ways that imbalance could occur. One is if you plan for there to be imbalance. If I say I'm going to send 10% of the traffic to the treatment group and 90% to control, that's no problem. The problem is if the sample sizes that you see in the data don't match what you expected to see based on the probabilities that you assign people with, that indicates some problem that you need to figure out what's going on. Okay, I had a, well, anyway. So if there's something unexpected, you need to track that down and figure out what's going on.
Yeah, that concludes all the questions so far from the Q&A session so far, and back to you, Dr. Hesterberg.
Okay, now we turn to resampling. And I'll begin with a general introduction to resampling, then look at what resampling tells us about the central limit theorem, and this may surprise a lot of you, and then turn back to resampling for A/B tests in general and for covariate adjustment in particular. So for one example data set, we had 1,600 observations from, let's think of this as the control group, and 23 observations from another group. The average repair time for observations in this group was 8.4 hours and 16.5 for the other group. Is that difference statistically significant? This arises from repair times for telephones. And in the example data, we have 1,600 observations in this group, and we can see that the repair times are quite skewed. There are a few large observations. And similarly, in the smaller group, the observations are skewed. So maybe the difference in means is kind of just due to this one large observation in that group. But even aside from that single observation, if we do a normal probability plot, we see that observations in the CLEC group tend to be somewhat larger than corresponding quantiles of the ILEC group. So maybe there is more going on than just that one observation. So here's the basic bootstrap procedure. We have a data set of size 1,600. We draw a sample of size 1,600 with replacement from that data. And we call this a bootstrap sample or a resample. And we calculate the sample mean for that resample. And we do that a bunch of times, say 10,000 times. And we get 10,000 random means. And those means are what we call the bootstrap distribution. And here's what that looks like for that particular data set. For the 1,600 observations with a mean of 8.4, the bootstrap distribution looks pretty normal and spread roughly 7.5 to 9.5. And a normal probability plot says that looks pretty normal. For the smaller group, 23 observations with a mean of 16, the bootstrap distribution is much more spread out. And there are two reasons for that. The biggest reason is the sample size is just smaller, and so there's more variability in the mean. The second reason is that the standard deviation for that data set was somewhat larger. We also see that this distribution doesn't look very normal. There's noticeable skewness in it. And this is sort of saying that, well, with a sample size of 23, the central limit theorem isn't working very well. Okay, if we just had 7 more, we'd be fine, right? Well, maybe not. The bootstrap standard error is the standard deviation of the bootstrap distribution. So back on this page, when we see this distribution, it's natural to calculate a standard deviation for that as a measure for how much this distribution varies. And that is now not the variance of observations, it's the variance of the sample mean, of these random sample means. So that's a standard error. What does a standard error mean? It is the variance of a statistic of the sample mean. And the bootstrap bias estimate is the average of the bootstrap distribution minus the observed value. Here we're dealing with standard, with means, so there's no bias other than just some randomness because we're doing random sampling. So the standard error for the mean of the larger data set, of the 23 observation data set was 3.9. It's much larger than the standard error for the large data set of 0.35. The idea behind bootstrapping is the plug-in principle, and this is something that is common in statistics. The variance of a sample mean is sigma squared over n. Its standard deviation is sigma over square root of n. In practice, we don't know sigma, so we substitute an estimate for sigma, and our standard error for a mean is s over square root of n. We use that idea in bootstrapping, but what we're plugging in now is not a single parameter like s for sigma, but a whole distribution. So here's what we would love to do. There is some population out there. We would love to draw many samples from that population and calculate a statistic of interest, a mean, a regression slope, what have you. for each of those samples, collect those statistics, and that gives us the sampling distribution. But we can't do that, right? We only have a single sample from the population. So what we do in bootstrapping is we plug in an estimate for that population, and maybe that estimate is the empirical data, and we draw samples from the empirical data, calculate the statistic of interest for each, and collect those. And this gives us then the bootstrap distribution. So what to substitute? Okay, again, the plug-in principle is the underlying population is unknown. We'll substitute our best guess. We have various options. We can just use the sample from the observed data. This is the ordinary bootstrap. If we believe that we should have a smooth distribution, a continuous distribution, we could smooth our data, and this would give what's called the smooth bootstrap. Or if you believe that the observations come from some parametric distribution, like an exponential distribution, you could draw samples from that. You could estimate parameters for your distribution from the data, and then draw from normal or exponential using those parameters. Or in some cases, we want to satisfy some additional assumptions. For example, if we're doing hypothesis testing, we want to sample in a way that would satisfy the null hypothesis. Okay, and the sort of underlying idea of the bootstrap is that this substitution works, but not always. And one thing in particular that I want to note is if we compare the true sampling distribution with the bootstrap distribution, the center is different. The spread is about the same, the shape is about the same, but the center is different. And that is kind of a key thing to keep in mind. The bootstrap is not used to get a better estimate of the population mean. The bootstrap samples are centered at X bar. They're not centered at mu. So the bootstrap isn't giving us something for nothing. Some people are suspicious of the bootstrap because they think it's something for nothing. We're creating data out of nothing and then taking the average of that, and there's got to be something suspicious about that. And the name bootstrap doesn't help. Why did Brad give it this name? Where the name comes from is The Adventures of Baron von Munchausen, a fantastical story where the Baron has all these adventures. And at one point, he's stuck in the bottom of a well and he's gonna drown until he comes up with the idea of pulling himself up by the bootstrap to escape the well. Something out of nothing. Voila. Okay. But that can make people suspicious, that implication. Well, it's really not doing that. It's not creating a better estimate of the mu from the data. It's only being used to estimate how accurate that estimate is. Are there any questions at this point?
We do not see any raised hands, but we have several questions in our Q&A session. So the very first question is the analysis being done in real time or just at a single time or maybe monthly from Madeline?
So for the Instacart experimentation platform, we normally run the analysis of experiments 3 times a week. but people can override that if they need more frequent analysis for a particular experiment.
The second question is covariate and adjustment is a prominent topic in clinical trials, with which current research conferences, regulatory agency guidance, and such. And nobody seems to talk about conditional bias. Focus seems to be entirely on reducing variance. Any thoughts about why that might be?
Why are people not talking about conditional bias? I guess thinking about variance reduction is an easier way to think of it for most people. And if you're doing the covariate adjustment, great. If you don't do it, then you have conditional bias. So this conditional bias interpretation of it can be useful if you're trying to convince people that you should use it. We want to avoid the conditional bias.
Then the next question is, this question is a bit vague, but it should be referred to one of the previous slides. Is the n equals 16, 64 plus 23 here, probably in one of the slides? I don't know if you have that. Mhm.
Yes, what we are doing here is we have 1664 observations in one sample and 23 in the other. And everything that I'm doing now during this section of the talk, we are bootstrapping the two groups independently. So we're drawing samples of size 1664 from this data set and draw samples of size 23 from this data set. Right now, we're not combining the data at all. We're treating both groups separately.
Yeah. Thanks. And the next question is, what do you need to do to the bootstrap to assess the null hypothesis? I'm referring something you said very briefly and not quite.
Yes, and I'll come back to that later.
Yes. Okay. Then the next question is, why not fractional random weight bootstrap from Reinhardt?
That is an option that's beyond the scope of this talk. I'm just giving an introduction here and not trying to be comprehensive.
Yep. And that concludes all the questions. Please move on, Dr. Hesterberg.
Great. Okay. Two sample bootstrap. Given that we have independent samples from two populations, we sample independently. Draw samples of size N1 from the first sample, N2 from the second sample independently. We calculate the mean from each of those samples and calculate a difference in means. And the 1,000 bootstrap samples are the bootstrap distribution. That is when we have independent samples. If instead we have paired data, then we would draw a sample from the pairs. So the bootstrap distribution for the difference here looks like this. It's centered at the difference between the original means. And it's got variability and skewness, which is largely driven by the small sample. You can think of it roughly as that big sample was large enough that the estimate is pretty accurate. So when we take y bar minus x bar and x bar is nearly fixed, all of the variability then comes from y bar. So even though there was a lot of data in one sample, the variability and the shape, the fact that there's still skewness, comes from that small sample. It's interesting to compare the difference in ordinary means to the difference in trimmed means. With data like that has outliers, we might think that we can reduce variance by using trim means, which are less sensitive to outliers, and indeed we could. The bootstrap distribution for trim means is much narrower in this case, with a standard error of 2.7 instead of 3.9. So you can use bootstrapping to help you decide what statistic to use. Should I be using a trim mean or a median or something else? Resampling in general, for the most part, we want to mimic real life. We substituted an estimate for the population. We substituted the data for the population. And then we did everything else, the sampling and the calculating the statistic, just like real life. If we did stratified sampling in real life, then we would do stratified bootstrap sampling. And one case where we don't mimic real life is that when we want to respect constraints like a null hypothesis, and I'll be coming to examples of that. So, for example, now we want to do a test for are the two samples the same? And in particular, a permutation test. My null hypothesis now is going to be a little different than you may be used to. Instead of H naught being mu1 equals mu2, the null hypothesis here is there's no real difference between the two groups. Any observation, if the null hypothesis is true, if the treatment has no effect, then any observation could have come from one group as well as from the other. And now the way that we resample is we pool the data and then we randomly take N1 observations out of that to label as group 1, and the other observations label as group 2. And the name permutation test comes as this is equivalent to putting all observations into a single vector, permuting those observations, and then taking the first N1 observations to be group 1. So here's what we get when we do that for the data set. We combine the 1600 and the 23 observations, and then randomly pick 23 out of that to be labeled as the CLEC group, take the difference between CLEC and ILEC means, and do that many times, and we get this permutation distribution. And one big difference between now and before is that this is centered at 0. This is consistent with the null hypothesis that there's no difference between groups. If we pool the data and then randomly split the data in this is what pure random sampling gives us in terms of variability for the difference in means of the two groups. This is where the original difference in means was. This fraction over here is our estimate of the p-value, the probability that pure random sampling would give us a difference this big. And just to compare the bootstrap distribution, which was centered at the original difference in means, and the permutation distribution, this is now centered at 0. And the p-value that we get using 500,000 observations is about 0.18%. A nice thing about this is that we can work directly with the difference in means. We don't need some other statistic like a t-statistic, so it's kind of more natural to do this. Just to compare, if we do a pooled variance t-test, we get a p-value of 0.045%. Permutation test gives us 1.8%. And in this particular context, the cutoff for significance was 1%. So the permutation test tells us the difference is not significant at the 1% level. A pooled t-test would tell you it is. Okay, which do we trust? They're different by a factor of 4. Well, the answer is we trust the permutation test. Flash back to Sir Ronald Fisher. who argued that the t-test is valid to the extent that it approximates what the permutation test would give. The permutation test answer is correct. The t-test is only an approximation. The permutation test was computationally infeasible using the computers of the day, who were young women. Okay, we don't have that same limitation now. We can use the more accurate permutation test rather than the approximation. Okay, are there any questions on this before we move on?
We do not see any raised hand, and we don't have any question asked in Q&A session. And I guess
Okay. Okay, now, common statistical practice is if sample size is at least 30 and the data is not too skewed, can we rely on normal approximation, t-tests, and so on? Usual answer is yes. And if not, well, we'll just use them anyway, because what else can we do? Well, how big a problem is this? No. Statistical theory tells us that if the population is normally distributed, then X bar and S are independent, and the t statistic has a t distribution. But these two things don't hold if the population is not normal. X bar and S are not independent. And by bootstrapping, we can get an idea of how badly that's violated. This is with the large data set, 1,600 observations. The x-axis here, each point corresponds to one bootstrap sample. The x-axis is the mean of the bootstrap sample. The y is the standard deviation of the bootstrap sample. And the bigger the mean, the bigger the standard deviation. This correlation does not go away as the sample size increases. When you have a skewed distribution, the more observations you have from that long tail, the bigger the mean and the bigger the variance. And t statistics don't have t distributions. And this tends to get better, closer to t distribution as the sample size increases. But we'll see later how quickly that happens. So the bootstrap, we can actually estimate the distribution of a t statistic by bootstrapping. A t statistic is defined as x bar minus mu over s over root n. We can take the mean of the bootstrap sample minus the mean of the population that we drew from, i.e. the mean of the original data, divided by standard deviation from the bootstrap sample. Calculate this for many bootstrap samples and get the distribution. So if we do that from the 1,600 observations, we get this distribution for the t statistic. And here's a probability plot of it. The x-axis is the y values are what we actually got, and this line is what we would expect if it were really a t distribution. And it's roughly linear, except that it's not close enough. If we actually do the calculation, how far is this distribution away from a t distribution? We see that 3.9% of the bootstrap t statistics are below the quantile of the t, the 2.5% quantile. So we've got 1.5 times as many observations in that tail. And this is with a large sample, 1,600 observations. So t statistics don't have t distributions. So the idea behind the bootstrap t interval is we're not going to assume that a t statistic has a t distribution. Instead, we're going to use the bootstrap to estimate what that distribution actually is. and then use that. Instead of using the usual quantiles, we'll use the bootstrap quantile to get the endpoints of our interval. So instead of x bar plus or minus 2, we'll do x bar minus 1 value and x bar plus another value. Okay, 1,600 observations is not enough for a t-interval to be accurate. We've got a one-sided non-coverage of about 3.9%. Is this a general problem for mean for skewed populations and other statistics? How big does n actually have to be before t-intervals are accurate? So say that my goal is I want to be 10% accurate. So I'm doing a 95% interval. I'm supposed to miss 2.5% on each side. I'm willing to be between 2.25% and 2.75%. And suppose that the population is actually exponential. How big would n have to be to get reasonable accuracy? So pick a number in your mind. What do you think n would have to be reasonably accurate here? 30 observations, 50, 100, 200. Well, what do you think? Now, if we were in person, I'd ask for a show of hands here, but skip that now. The answer turns out to be 5,000. The central limit theorem operates on glacial time scales. It does not happen quickly. This plot is the one-sided non-coverage for a t-interval. The top curve is on one side, the other curve is on the other side. And for a bootstrap t, it is much more accurate. And then a bootstrap percentile interval is a little bit in between, but really not great. And the difference between the two sides is that I've just rescaled the x-axis differently to focus on 5,000 being where roughly the t-interval becomes accurate enough, within 10%. Okay, why do people not realize that t-intervals are so awful? Well, for one thing, you kind of need bootstrap diagnostics to understand that, and statistics was developed before we had bootstrap. You also need to use a lot of bootstrap samples before you'll actually notice any deviations, and you need fast computers. If to do some of the simulations that I did, I would have needed 20,000 hours of computer time using the department VAX when I was a grad student. Beginning grad studies in 1981. And we've got sour grapes. People have learned to accept low accuracy and to kind of adjust their mental model of what's acceptable based on what they thought was practical. The inaccuracy is partly known. It's known for the sample mean using Edgeworth expansions. There's a 78 JASA paper that provided skewness adjusted t-statistics for one sample, but it never really took off. And then the other thing is that two sample t-tests aren't as bad as one sample t-tests. If you have two samples and the sample sizes are equal size, then when you take y bar minus x bar, one of those is positively skewed. They're both positively skewed, and when we take the difference, the skewness tends to cancel out. So two samples t-statistics with equal sample sizes are reasonably accurate much quicker. Okay, are there any questions at this point?
I do not see any raised hand, but there are several questions from the Q&A session. And it is started with Reinhardt. The variance in the permutation distribution seems to be the sum of variance within the groups and between groups identical to large. Is that correct?
let's see. No, we'll look here.
Yeah.
This is the permutation distribution. The variance here would correspond to, yes, we are pooling the data, so it combines variance between groups and variance within groups.
Okay. Yep. The second question is, with related to the permutation example, is the take-home message that the pooled T result was mostly driven by the small sample size in the CLEC?
Yes. Mm-hmm.
Yep. And the next one is from Guodong. When you resampled from two groups, and these two samples are not balanced, the sampling with replacement will place on more weight on group with smaller sample size. Do you think it is acceptable?
So we have the unequal sample sizes, and we split the data with the same sample sizes as the original data. And I'll point out one thing about that and then come back to that question. We pooled the data and then split the data. We sampled without replacement. We drew 23 observations from that to label as CLEC. Another way that we could sample is we could pool the data and then sample with replacement. Draw 23 observations with replacement, label those CLEC. Draw 1,600 observations with replacement, label those ILEC. The permutation test is preferred. Imagine that there are, say, 5 outliers in the original data. When we do the permutation test, sampling without replacement, we have exactly 5 outliers. They're somewhere within the two groups, but it's always exactly 5. If we were instead to do the bootstrap, the resampling with replacement, there would be a variable number of observations. It could be 5, it could be 3, it could be 15, etc. The variance that we get with the permutation test gives us the variance that occurs when there are exactly 5 observations, which is what we had. So given that we have 5 observations, the permutation test tells us the variability. So it's best to do that sampling without replacement. Now, the question was, is it appropriate to do this unbalanced sample? And the answer is yes. The real data had unbalanced sample sizes. And so our sampling should mimic that. We want to reflect what happened in real life. Okay. Next question.
Yeah, the next question is, does Bootstrap depend on the ability of the data to represent the CDF? If so, would 23 samples be enough to get a decent empirical CDF? From Chris.
Okay, so the question is, the Bootstrap uses the empirical data to reflect the population. Here we have the empirical data in the top left, and here we have the true population. And the answer is yes. The Bootstrap tends to work better when we have enough data so that the Bootstrap CDF, the empirical data, closely matches the true CDF. Now, there are different Bootstrap methods which are more or less sensitive to the size of the original data. The Bootstrap T distributions, for example, work pretty well for small data sets. Some other Bootstrap methods don't work as well. In this figure, for example, the short dotted line was the accuracy of the Bootstrap T procedure. The other dotted line is the accuracy of a bootstrap percentile interval. The bootstrap percentile interval is you just take the middle 95% of the bootstrap distribution as your confidence interval. That isn't as accurate. So the answer is yes, the bootstrap relies on the empirical CDF to represent the population CDF. Yes, that works better with larger sample sizes. And different bootstrap procedures are more or less sensitive to small sample sizes. Another point is that N is the size of the original data. This tends to be much more important than the number of bootstrap samples. I talked about taking 10,000 bootstrap samples. It's good to do that, but in many contexts, we can get by with many fewer than that. That's not as sensitive a matter. Results are not as sensitive to the number of bootstrap samples as they are to N. Okay, any other questions?
Yep, there's one more question left, and it is not asking very clearly, but I'll try to frame it as clear as I can. The question is from Alan, but for 5 outliers, n equals 5 is also a random variable. And could you help us understand like how would that contribute to the test?
Okay. When we do a hypothesis test, we want to answer the question, could the difference in means be due just to labeling, or is there some real difference between the groups? Given the data that we have, the 1,600 plus 23 observations, is the difference in means. Can we be confident that that is more than just random chance? So when we do that, we take the data as given, the observations that we have, including the fact that we had 5 outliers. That's appropriate for a test. Is the difference due just to random sampling, given the data that we have? If, on the other hand, we wanted to do confidence intervals for the difference that we might get with other data, then we would not want to constrain to having exactly 5 outliers. Then bootstrap procedures would be more appropriate, allowing the number of outliers to vary.
Yep. I guess there's one more question popped up from Jeffrey Corbin. You said making a confidence interval using just the bootstrap distribution is better than using bootstrap T. Is that correct? Or am I understanding that correct?
No. The bootstrap percentile interval, which is just the range of the middle 95% of the bootstrap distribution, is not as accurate. Here, the inaccuracy of that bootstrap percentile, we want to miss 2.5% of the time on each side, and on one side it misses over 5% of the time. Much worse than the bootstrap T procedure.
Okay, that concludes all the questions. Please move on.
Okay, we move on to A/B testing, and we'll look at 4 cases, interesting things. 1, coming back to ratiometrics. Now, remember, before I lead into some of the twists, a little more background on bootstrapping. Some variations when we do the ordinary bootstrap, we sample with replacement from the original data. And we can think of that in terms of how many times each observation is included. Observation 1 from the original data is in the bootstrap sample 3 times. Observation 2, not at all. Observation 3, once, etc. So those frequencies have binomial distributions with parameters n and probability 1 over n. We could instead do the Poisson bootstrap, where we assign frequencies to the observations using a Poisson distribution with lambda equal 1. So on average, any observation is included in the bootstrap sample 1 time. So in doing that, the frequencies are independent, but the total sample size may not equal n. This can be more computationally efficient in large samples because of this independence. Another option is half sampling, where we sample with replacement, without replacement, but with sample size n over 2. Basically, take a random half of the data set. It turns out that that gives you the same standard error as the ordinary bootstrap. Yeah, the sample size is half as big, but we've got a finite population correction factor that reduces the variance by a factor of a half. So those cancel out, we get the same standard error. So it's a little more computationally efficient. We get the same standard error. We do lose the skewness, so we aren't learning as much as we would with the ordinary bootstrap. And then a variety of other methods, the jackknife, the group jackknife, etc. We'll see jackknifing in a bit. Turning back to the topic of ratio estimates, dollars per order, which is the sum of all dollars spent divided by the number of orders. And if we wanted to do the delta method approach for this, this would be the sum of the GMV per customer over the number of orders per customer. So we would, in this case, we would want to bootstrap the customers, the unit of randomization. So another way that ratio metrics come about is when we do experiments, we tend to look at the relative lift of the experiment. What is the difference between the treatment and the control divided by the control value? And that's just a ratio subtracting 1. So both of these cases are cases where we need to work with ratio estimates and get standard errors, confidence intervals for these. So in doing this, in bootstrapping relative lift, when we're analyzing an experiment, we could either bootstrap the observations, or we might want to do a parametric bootstrap. We might want to calculate the standard error for the variant for the treatment group and the standard error for the control group. And treatment group and control group are independent. So we can independently generate values for the treatment group from a normal distribution. If our sample sizes are large enough, then the variability is approximately normal. We could do a parametric bootstrap. Now, turning to confidence intervals, suppose we're looking at the ratio, y bar over x bar. If we did a t-interval, it's going to be symmetric. Estimate plus or minus 2 standard errors. We could get the standard error by bootstrapping. We could get the standard error using the delta method. Whichever those we use, we sometimes have a contradiction where the t-interval includes 0, but the difference between treatment and control groups is statistically significant. And this is a little screenshot from our experiment output where we had a relative lift of 180%. P-value indicates it's quite significant, but the confidence interval included 0. What's going on here is that t-intervals are symmetric, and that's not really a good idea when you're working with a ratio estimate. It is fine for large enough samples, but can give you contradictions like this. And so let's look at a couple of alternatives. One is the bootstrap percentile interval. Remember, this is the middle 95% of the bootstrap distribution. So in the right figure here, what we have is the original estimate, the control mean on the x-axis, the treatment mean on the y-axis. Then we have a bunch of bootstrap observations, the little points. And the way that I generated these here was with a parametric bootstrap. plus or minus normal variation calculated from the standard error for control and the standard error for treatment. So then when I'm looking at the slope, the ratio y bar over x bar, I look for the line that has 2.5% of the observations below it. And I look for the line that has 2.5% of the observations above it. And that then gives me a confidence interval for the slope. And in this case, it's quite wide. There's a lot of variability here, relatively small sample sizes. Okay, so this bootstrap percentile interval gives me a confidence interval for the slope. And the confidence interval is quite asymmetric. If you think in terms of slope, this slope isn't much smaller than this slope, the slope for the original data. On the other hand, the upper endpoint is much larger. There's also a parametric version called Feeler confidence intervals, in which we create the confidence ellipse, standard error, directional standard error times 2, and let the confidence interval be the tangent of the lines through the origin and tangent to that ellipse. So this will tend to give similar answers as the bootstrap percentile interval. They'll differ a little because of random variation. And both of those are very different than the delta method interval, which T interval with delta method, which is symmetric in terms of vertical distances here. So we now, in our experimentation platform, have switched to using Feeler intervals rather than T intervals. This is just another view of Feeler intervals. You take the tangents of the confidence ellipse. And in contrast, the delta method is just kind of geometric voodoo. Let's not even waste time on it. Next, let's talk about large data. We want to avoid expensive group by operations where we have to calculate GTV per user and orders per user with a group by user. And we do that instead using the group jackknife, where we group by the bucket. We could also use the Poisson bootstrap. Won't deal with that. But let me show you what the jackknife does. We split the data into K buckets, omit one bucket at a time, and then our standard error estimate is the standard deviation of those values, and then rescaled. So instead of, you're probably used to this quantity, summation of value minus mean squared, divided by, in this case, it would be K minus 1. This is much larger because we're rescaling it. The reason that we're rescaling it is the jackknife values, jackknife samples are quite similar to the original data. Imagine that we let K be equal to N. So we omit one observation at a time. Then a jackknife sample is N minus 1 observations out of the original N. That sample is almost identical to the original sample. It differs only by one observation. So the answers that you get for theta being sample mean or whatever are going to be very similar to the original answers. So we can't just take the sample standard deviation of those. It would be too small. We need to rescale. So it's a relatively simple formula. And we now calculate standard errors in our platform using jackknifing, this group jackknife. We produced, now turning to a kind of an ugly twist, which is we calculated jackknife estimates. This is development work. jackknife estimates of the standard error for covariate adjusted treatment control groups, and they were all wrong. The variances are too large, and the treatment control estimates weren't independent. And what happened was kind of an interesting twist. We needed to compute conditional standard errors. So turning back to covariate adjustment, remember that we produce estimates for the treatment group and the control group by taking predictions at the common mean at X bar. So here I have the formula for control group, would be similar for treatment group. And when we calculate standard errors for determining whether our difference is statistically significant, we do it conditional on that X bar. So what we first did was sort of the usual black box approach, where we take a bootstrap sample, we pass it into our subroutines for calculating covariate adjustment and get estimates out. And that would do what I have at the bottom here, alpha hat from a bootstrap sample plus beta hat from the bootstrap sample times X bar from the bootstrap sample. And what we instead need to do is use the X bar from the original data. And the reason is, when we do analysis of an experiment, we're doing our analysis based on the data that we have and the X bar that we had. When we're looking at variabilities, we are looking at variabilities given this X bar. We're not talking about what might happen in the future with a different data set and a different X bar. This is what we have with this X bar. So once we realized what was going on, then it was straightforward to fix this. And this is one example of case where tests and confidence intervals do not always agree. A few examples. When you do a two-sample t-test, it may be reasonable for your test to assume equal variance. If the null hypothesis is true, then the two groups, the two distributions are the same. But when we're not testing, when we're doing a confidence interval, we're asking what would happen if the two groups aren't the same. Then we should not assume equal variances. When we do a permutation test, to do the permutation test, we have to assume that the two groups have the same distribution. But if we're going to do a confidence interval, okay, can't do a confidence interval with the permutation test. We do it some other way. Confidence intervals won't assume the same distribution. And finally here, for covariate adjustment, the tests assume that the true means for the control group and the treatment group are equal to the X bar that we had in the observed data. But confidence intervals for future experiments shouldn't assume that we'll have the same X bar. I'm going to switch this because we're just about out of time. I want to wrap up. Just for review, we looked at covariate adjustment, then we looked at resampling, starting with the one sample bootstrap and the idea behind this, plugging in a population. Two sample bootstrap and the permutation test. We looked at the central limit theorem. And for one sample t-test, you need, if there's any skewness, you need much larger samples before the standard t-interval is reasonably accurate. You should use a bootstrap t or a skewness adjusted t-statistic. And then we looked at resampling for A/B tests, case of ratio metric, large data stuff, and covariate adjustment. And if you want more information on resampling, check out my website. And there's some documents there that you can download. And then there's also information on my book. That's it. Are there any additional questions? I want to thank you for sticking around. Hope you enjoyed it.
Yeah, and thanks Thanks, Dr. Hesterberg. And there's no raised hand, but there's one more question in the Q&A session, and I'll appreciate if you could probably spend some extra time to answer it. Is a question from Guodong. When you talk about the bootstrap, the endpoint distribution, where is the covariate and what's its role?
So when we talk about bootstrapping in the context of covariate adjustment, if the original data looked like this, then when we do bootstrap samples, we would sample independently from the treatment group and from the control group. So the bootstrap distributions would have the covariate on this axis and the metric that we're measuring on this axis. It would be basically, it would look like these distributions, but some of the points would be included 1 time, 2 times, 3 times. Many of them would be included 0 times. Each point would be included some random number of times. So a bootstrap distribution looks pretty much, the bootstrap sample looks very much like the original sample. And then for each bootstrap distribution, we calculate the statistic, the covariate adjusted estimate, and collect those.
Yep. There's just one more question popped out. I don't know if you would like to answer it or probably prefer to answer it through email.
Let's hear the question and we'll see.
Okay, sure. This question is from Jacob. Is it possible to work as a data scientist and Instacart without a PhD in statistics or master PhD in data science?
Yes, most of our data scientists do not have PhDs. Some people won't have masters either. They may have degrees in other fields.
Okay.
Yeah, data science spans a gamut from the more statistical end to the more software engineering end. And so there are positions for people with different skills.
Yep. Thanks for the great session, Dr. Hesterberg, and we have learned a lot from that. And that concludes all the questions. And again, thank you so much for presenting the great work again. And yeah, let's move on. And for the audience still in the meeting room, if you have any further questions you would like to ask, or if you would have any other things you would like to discuss with Dr. Hesterberg, please find his email in the chat, which I'm going to share very soon. And thank you.
Thank you, Frank.